Okay, we're going to start by showing the power series, the sum from n equals 0 to infinity of sine of x to the nth power over n factorial converges, for all x. And this is real x. We're not dealing with imaginary numbers. Okay. So, what we're going to do, first part of our solution, we're going to let x be a real number. And you might notice that all of the proofs start just like this. It's because we're trying to show that this is true for all real x. Okay. The series, the sum from n equals 0 to infinity of the absolute value of sine of x to the n over n factorial has no negative terms. Okay. We had to do this. We had to put absolute value symbols around our sequence here so that we can refer back to a direct comparison test. Now this will relate to absolute convergence, but now we are working with something that's non-negative, right? So sine of x for some x values can be negative, right? For values of x that drop us below the x-axis, we have a negative output. So we had to cover this, and so now we're actually going to work with this. Okay. Not only does it have no negative terms, but it is less than or equal to the sum from n equals 0 to infinity of 1 over n factorial. And you can see that because sine of x is always less than 1. So really what we did there was we knew that that's always less than or equal to 1. When you raise 1, the greatest value of that, to any power n, as n goes towards infinity, you're still going to get 1. Right? So it's always going to be less than this. Right? Correct. Which we know converges to E. It converges to E. You would know that by looking at the Maclaurin series. Okay? It's centered at x equals 0. It's a Maclaurin series. Right? The Maclaurin series is x to the 2n. So that converges to e to the x. What we've replaced by x is 1. So in e to the x, we'll replace x with 1. You just get e to the first power, or e. So we have to be able to recognize some manipulations of our Maclaurin series to be able to do this. Okay. Now, we're not quite done yet. We do know that the absolute value of our function converges. And now we're going to conclude that the whole thing converges. Okay. To do that, I'm going to say, therefore, the absolute value, the sum from n equals 0 to infinity of the absolute value of sine of x to the nth power over n factorial converges by direct comparison. That's what we compared this to. Right? We knew that sine of x was less than 1, so we could just substitute that in there and just refer back to that. Now, you can see that it's a little different than it looks here. Right? We've lost absolute value bars around the denominator, and that's because n is always positive, so n factorial also always positive. N is always positive here, so we don't have to worry about that being positive. We just talk about the absolute value of sine of x. Okay, so now we have that this series converges by direct comparison, excuse my period mark, and this series, starting at n equals 0 to infinity, of sine of x quantity to the n over n, excuse me, n factorial converges absolutely. That is the end of my proof. I get my little QED box and I am done. Sorry, what was your question? Why does the last sentence or the last x do that? Because this is what we are asked to prove converges, so we need to refer back in the end to this function through a string of tests that we used. First, it's good to just review what we did. We slapped on our absolute value symbols so we can make it non-negative, so that way we can use the comparison test. And since we had to slap on absolute values and refer that, the absolute value of our series, compare that to a series that is convergent, then we know that our original series converges absolutely.
So to get to there, you would have had to know that 1 over n factorial is the trick thing for the x.
This step was the trick, recognizing that this is convergent. That will be the trickiest parts of this proof. Besides that, you pretty much follow the script that I just said.